Good morning. In the last class, we considered fixed point iteration method for solving equations of the form f of x is equal to 0. Before connecting the fixed point iteration method with the root finding problem, we defined what we mean by a fixed point for a given function in an interval. We said that p is a fixed point for a given function g if g of p equal to p, where g is defined in the interval a b. Then we presented the sufficient conditions for existence and uniqueness of a fixed point in an interval a b for this function g, and said that g must be a continuous function in the interval a b and g takes values in that interval a b. Then it has a fixed point, and in addition, if g dash of x exists in the open interval a b and there is a constant k with 0 less than k less than 1 such that modulus of g dash of x is less than or equal to k less than 1 for every x in the open interval a b, then this fixed point p is a unique fixed point for the function in that interval. And then we presented the error bounds on the approximation to this fixed point, which we obtain by generating a sequence of successive iterates using Pn equal to g of Pn minus 1 for n greater than or equal to 1, where g satisfies all the conditions that we have listed here, namely g satisfies conditions of the fixed point theorem. Then we showed that the sequence of iterates generated by this converge to a unique fixed point p for the function g. So, having understood the fixed point problem, we tried to connect this problem with that of root finding problem. What is a root finding problem? In that we will be given an equation of the form f of x is equal to 0, where we are required to find a root of this equation or a 0 for the function f. So, we said that we will rewrite this equation f of x is equal to 0 in the form f of x is equal to x minus g of x equal to 0. So, if p is such that f of p is equal to 0 and p is a root of the equation, then we observe that at this p we have p equal to 0, implying that g of p equal to p, so that p is a fixed point for this function g. So, if p belongs to an interval a b, then we have a fixed point for the function g in that interval, and it exists and is unique provided g satisfies certain conditions, namely if g satisfies the sufficient conditions specified, then the sequence of iterates generated by Pn equal to g of Pn minus 1 will converge to this fixed point p for the function g, and that unique fixed point is going to be a 0 for the function f, or a root of this equation f of x is equal to 0. So, we tried to see how can we write f of x in the form x minus g of x. Can it be written in a unique way? We just considered an example and said that there are several ways in which f of x is equal to 0 can be written in the form x is equal to g of x. Then we considered each of these forms and said that in some cases there is no reason why we can believe that the fixed point theorem will give a sequence of iterates which will converge, because g did not satisfy the conditions of the theorem, and in some other forms we were able to show that g satisfies the conditions. And we also made a remark that if we take our g of x to be in the form x minus f of x divided by f dash of x, then this form will converge rapidly to a unique fixed point for the function g, and therefore rapidly to a 0 of the equation f of x is equal to 0. So, we would like to look at this form in this class and see whether this method converges rapidly and what is the order of convergence of this method when we rewrite the given equation f of x is equal to 0 in the form x is equal to g of x, where g of x is given by x minus f of x by f dashed of x. So, before doing all this, let us define the order of convergence of a fixed point method. So, if g is such that g of x is equal to x and that g is continuous on the interval a b with continuous derivatives in the interval a b, which is an open interval. Further, point for this function g in the interval a b. What does that mean? Is equal to p, and if this g is such that g dashed of p, g double dashed of p, etc. up to g to the alpha minus 1 at p, they are all 0, and the alphath derivative of g at p is different from 0. Then we say that the fixed point method given by g of x is equal to x has convergence of order alpha. So, let us just see the definition again. So, you are given a fixed point method g of x is equal to x, and you observe that g is continuous on the interval a b and it has continuous derivatives. So, we can also say that it has continuous derivatives g dashed, g double dashed, etc., say up to order alpha in the open interval a b, and p is a fixed point for g in that interval. So, that g of p is p. If g is such that its derivatives up to alpha minus 1th derivative evaluated at p is 0 and the pth order derivative is different from 0, then we say that this fixed point method g of x is equal to x has convergence of order alpha, or the order of convergence of the fixed point iteration method is alpha. Let us consider the following result. Let g be a continuous function in the closed interval a b, and it is such that g of x takes values in the closed interval for every x in a b. In addition, g is such that g dashed is continuous on the open interval and there exists a positive constant k less than 1 such that mod g dashed of x is less than or equal to k for every x in the open interval a b. We now show that if g dashed of p is different from 0, then for any number p naught belonging to the closed interval a b, the sequence p n given by g of p n minus 1 for n greater than or equal to 1 converges only linearly to the unique fixed point. This is what we have to show. So, let us work out the details. So, what is it that is given? The first few conditions show that they are the conditions listed out in the fixed point theorem. So, we immediately conclude that by fixed point theorem, G has a unique fixed point P in the interval a b. And the sequence Pn equal to G of Pn minus 1 for n greater than or equal to 1 converges to this unique fixed point. We now have to show that the order of convergence of this method is 1, namely the method has linear convergence. This is what we have to show. What is it that is given to us? It is given that G dashed of P is different from 0. So, let us make use of this and then show that the method has order of convergence to be 1. So, now for each n, we know that Pn minus P will be such that it is G of Pn minus 1 minus G of P. G is a continuous function on the closed interval, G dashed exists in the open interval, and therefore, I can use mean value theorem and write G of Pn minus 1 minus G of P is some G dashed at psi n into Pn minus 1 minus P, where psi n lies between Pn minus 1 and P. And what do we know about the sequence Pn minus 1? It converges to P. So, limit as n tending to infinity of Pn minus 1 is P, and therefore, limit as n tending to infinity of G dashed of psi n is G dashed at P. So, we shall make use of this and take the absolute value of mod Pn minus P, which is this absolute value of G of Pn minus 1 minus G of P. So, that will be less than or equal to modulus of G dashed of psi n into modulus of Pn minus 1 minus P. So, in the limit we know that G dashed of psi n converges to G dashed of P. So, this is approximately G dashed of P in absolute value multiplied by Pn minus 1 minus P. So, what is it that we have shown? We have shown that Pn minus P in absolute value by mod Pn minus 1 minus P is approximately a constant C, where C is mod G dashed of P. So, we recall the definition of order of convergence of a method. What is it that we have shown? We have shown Pn minus P is the error at the nth step. So, that by the error at the n minus 1th step is a constant C. So, by definition, the power to which this is raised to gives you the order of convergence of the method. So, what we have shown is mod E n is C times mod E n minus 1, and then order of convergence of this method is 1. So, the method which generates a sequence of successive iterates and which converges to a unique fixed point for the function g converges linearly to the unique fixed point. What is the condition that we have used? Is g dash of p is different from 0. So, the result immediately implies that if we want higher order convergence for fixed point iteration methods, then this can happen only when g dash of p is equal to 0. The question now arises, is this condition that g dash of p equal to 0 alone is enough to ensure that we have higher order convergence for fixed point iteration methods? Let us see the following result and understand the conditions under which the fixed point iteration methods will have higher order convergence when the conditions that have to be satisfied by g include the condition that g dash of p is equal to 0. So, let us write down the result in the form of following theorem. The result is given by this theorem, which says that let p be a solution of the equation x is equal to g of x. What does that mean? G of p is p, so p is a fixed point for the function g. In addition, g dash of p is 0. So, g is such that its first derivative vanishes at p, which is a solution of the equation x is equal to g of x, and its second derivative is continuous with modulus of g double dash of x to be strictly less than m on an open interval I which contains this p. Then there is a number delta positive such that you start from any p naught which lies in the interval p minus delta to p plus delta. Namely, you start with a p naught in a neighborhood of this p, which is a solution of x is equal to g of x, and then consider the sequence of iterates generated by p n equal to g of p n minus 1. Then the result says that this method converges at least quadratically. And where does it converge to? It converges to p, and what is p? It is a solution of the equation x is equal to g of x, or it is the fixed point for the function g. In addition, it tells you that the error at the n plus 1 step E n plus 1 is such by modulus of E n square is less than capital M by 2. So, that also gives you the asymptotic error constant C in terms of capital M. And what is this M? M is such that modulus of g double dash of x is strictly less than M in an open interval that contains this P, which is a solution of the equation x is equal to g of x. So, you also have some information about what the asymptotic error constant is. So, the theorem tells us that the best way to construct a fixed point iteration problem associated with the root finding problem, namely f of x is equal to 0, is to consider the following, namely subtract a multiple of f of x from x. So, that if you consider the sequence of iterates generated by p n is equal to g of p n minus 1 for n greater than or equal to 1 with g of x given by x minus f of x into a function phi of x, where phi of x is an unknown function, it is a differentiable function that has to be determined such that the method g of x is equal to x has a fixed point P to which this sequence will converge to will have higher order convergence or will have quadratic convergence. So, let us try to find out this function phi of x, which is a differentiable function such that this method has quadratic convergence. What are the conditions that it should satisfy? When f of p is equal to 0, g dash of p must be equal to 0. You want the function g to be such that g must be of the form x minus f of x into phi of x, where phi of x is a differentiable function, it is an unknown to be determined in such a way that g dash of p is equal to 0, and p is a fixed point for the function g. So, let us write down what g is. So, g of x is x minus f of x into phi of x. So, g dash of x is going to be 1 minus f of x into phi dash of x minus x. So, g dash of p is 1 minus f of p into phi dash of p minus f dash of p into phi of p, and this must be 0. So, we know that f of p is 0 because p is a root of the equation f of x is equal to 0. So, this tells us that g dash of p is 1 minus f dash of p into phi of p, and we want this to be equal to 0. So, g dash of p is 0 if and only if your f dash of p is 1 by phi of p. But what do we want? We want to determine this function phi. So, phi of p is 1 by f dash of p. So, we take the function phi of x to be 1 by f dash of x, and this ensures that phi dash of phi at p is 1 by f dash at p. So, we have determined this differentiable function phi of x. So, we can take g of x to be in the form x minus f of x, and what is phi of x? It is 1 by f dash of x. And what do you see? You observe that this is nothing but your Newton-Raphson method. Why? X is equal to g of x, and g of x is x minus f of x by f dash of x. So, this is essentially Newton-Raphson method, and we have already established the order of convergence of Newton-Raphson method, namely the method by xn 1 xn minus f of xn divided by f dash of xn converges quadratically. Namely, it has order of convergence to be equal to 2. And that is why we made a remark earlier that. So, let us now define the order of convergence. Of a fixed point iteration method. So, fixed point iteration method is of the form g of x is equal to x. If g is continuous on the interval a b with continuous derivatives g dashed, g double dashed, and so on, and alphath derivative of g in the open interval a b. P is a fixed point for g. So, therefore, g of p is p, and if the derivatives are such that g dashed at p, g double dashed at p and so on, the alpha minus 1th derivative at p, they are all 0, but the alphath derivative of g at p is different from 0. Then the sequence given by Pn is equal to g of Pn minus 1 for n greater than or equal to 1. This is a fixed point iteration. This converges and has order of convergence as alpha. So, the conditions are that the first alpha minus 1th derivative of g at p must be 0. The alphath derivative of g at p should be different from 0. Then this method has convergence of order alpha. So, this is how we find the order of convergence of a given fixed point iteration method. And our discussion tells us that the Newton-Raphson method belongs to the class of fixed point iteration methods. So, let us solve the equation cos x minus x equal to 0. So, solving this problem is equivalent to solving the corresponding fixed point problem, namely find that x for which x is equal to cos x, or find that p for which p equal to cos p. Suppose what is that point p? If I draw the graph of y is equal to cos x and the graph of y is equal to x, the point where the line y equal to x crosses the graph of y is equal to cos x is the required point at which p is equal to g of p. So, if I draw the graph of y is equal to cos x, so at x is equal to 0 it is 1, and at x is equal to pi by 2 it is 0. So, this is the straight line y equal to x, and this is the point at which they cross each other. This point p is a root of the equation cos x minus x is equal to 0. So, let us take an initial approximation p naught to be pi by 4, which is 0.7853981635. Start with this initial approximation. So, I would like to solve it by fixed point iteration method, namely the method is going to be x is equal to g of x, where g of x is x minus f of x by f dash of x. We write down the successive iterates generated using Pn equal to g of Pn minus 1, and we observe that if we require the result correct to 2 decimal accuracy, then we observe that we are able to achieve the desired accuracy at this step. So, that at the 6th step we have correct to 2 decimal places, the answer is 0.74. In the 7th step, correct to 2 decimal accuracy, the answer is again 0.74. So, the fixed point to which the sequence of iterates converge to is given by p equal to 0.74, correct to 2 decimal places, and it is an approximation to the solution of the equation f of x is equal to 0, namely cos x minus x is equal to 0 in the interval 0 to pi by 2. So, we observe that Newton-Raphson method belongs to the class of fixed point iteration methods. So, in the beginning we said that we are going to develop numerical methods which belong to the following two categories, namely enclosure methods and fixed point iteration methods. And we have developed some methods which belong to enclosure methods, namely the bisection method and the secant method. And we have now a method which is Newton-Raphson method, which belongs to the class of fixed point iteration methods. So, given an equation of the form f of x is equal to 0 and we are interested in solving this equation numerically, then we can make use of any one of these methods which belong to either enclosure category or fixed point iteration category and solve this problem correct to the desired degree of accuracy. And we have discussed what is going to be the order of convergence of each of these methods. We have discussed the error analysis, and so the complete details about the error that occurs at each step of computation is known to us by the analysis that we have performed for each of the methods that we have discussed. So, in the next class we shall consider some problems based on these methods and see how we can solve these problems. We will continue in the next class.